All right, so this is 8.1, the distribution of the sample mean. So this first section especially is a lot of setting up the foundation, explaining what's going on. Starts off with the sampling distribution of a statistic. It's the probability distribution for all possible values of a statistic computed from a sample size of n. All right. The sampling distribution of the sample mean, which is x bar, is the probability distribution of all possible values of the random variable x bar computed from a sample size n with the population mean mu and standard deviation sigma. So when we put numbers on it, we'll probably look better and we'll be able to apply the process. So we'll put some numbers to it. All right, and then the third one, suppose that a simple random sample size n is drawn from a population with mean mu and standard deviation sigma. So the sampling distribution of x bar is going to have the mean that's going to be the same as your population mean. Notice it has, can I write on this? It won't let me magnify it. All right. Well, anyway, this sample mean, the sample distribution mean is going to be the same as your population mean. And then the way we calculate the standard deviation of a sampling distribution, we'll take the population standard deviation and place it over the square root of n, the square root of your sample size. And once again, it'll probably look better after we put some numbers on it. All right, the standard deviation of the sampling distribution of x bar is going to be called the standard error of the mean. So they asked you that in my math lab. That's the standard error. So this over here, standard deviation over square root of n, is considered your standard error of the mean. All right, and the last one for this page, if a random variable x is normally distributed, the sampling distribution of the sample mean is also normally distributed. So the reason why that is important is that because that allows us to use the z-score relationship, and that z-score chart. So the fact that it's considered normally distributed, that allows us to use the z-scores. That's why I wrote down in the red means that we can use the z-scores. All right, give you a chance to write that before we go to the next page. All right, is everybody good?
I'm still copying the last one.
All right, thank you.
Thanks.
Yep, no problem at all. Not a problem at all.
I'm still writing too.
Okay, just let me know when you're ready. It's not a problem.
I'm done now. Thank you.
Thank you. All right, so the next thing to go to is this example. It says if the IQ, not if the IQ, the IQ of humans is approximately normally distributed with the mean of 100, standard deviation 15. So we're talking about population of all humans. So, well, we're talking about all humans, so that is our population. So the mean is 100, standard deviation 15. Compute the probability that a simple random sample of size n equal to 10, results in a sample mean greater than 110. So first thing we do is that in this box, you notice we have everything that was given to us. Mean is 100, standard deviation is 15, sample size is 10, and X bar, our sampling distribution mean is 110. All right, give you a chance to write that out. All right, so then looking at the mean of our sampling distribution, notice that it's the same thing as the population mean, so it's going to be 100. Then to calculate the standard deviation of our sampling distribution, we take sigma, which was 15, place it over the square root of our sampling size, which is 10, and that gives us 4.743. Once we have those, then we can go ahead and find our z-score. Z-score formula, x bar minus we sampling distribution mean minus, hold up, sampling distribution minus the sampling distribution mean over the standard deviation of the sampling distribution. A little tongue tied. Anyway, 110 minus 100 over 4.743 gives us 2.11. And we always round our z-scores to 2 decimal places, so that's why we have 2.11. Then we go to the chart. So we're going to do the chart the same way we would do the chart in chapter 7. Look for 2.1 on the left column and 0.01 on the top row and see where they meet. And they meet at 0.9826. Now don't forget, whatever value we get from the chart, that's always going to represent less than. But we want it greater than. Notice, look at the word last sentence on our problem. It says greater than 110. So to find greater than, just like we did in chapter 7, we subtract that 0.9826 from 1. And that will be our answer. The probability of obtaining a sample mean IQ greater than 110 from a population whose mean is 100 is 0.0174. All right, any questions on the process so far? All right, everybody good? Can I go to the next page? All right. See a thumbs up, appreciate it. All right, the next one, central limit theorem. So we're still in we're still in section 8.1. Central limit theorem, regardless of the shape of the underlying population, the sample distribution of X bar becomes approximately normal as the sample size N increases. So remember, once again, the reason why this is important, because being normal distribution means we can use our z-scores. So if the distribution of the population is unknown or not normal, then the distribution of the sample mean is approximately normal, provided that the sample size is greater than or equal to 30. So if our sample size is greater than or equal to 30, we can assume that we're dealing with the normal distribution. And once again, that enables us to use our z-scores. All right, scrolling up. All right, so the mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Weight gain during pregnancy is skewed right. An obstetrician obtains a random sample of 35 low-income patients and determines that their mean weight gain during pregnancy is 36.2 pounds. I'm good to scroll up. Okay. Does this result suggest anything unusual? All right. Oh, I forgot, but the rest of the problem is actually on another sheet. So everybody's still copying this before we go.
I'm still writing. I'm almost done.
Okay, not a problem.
I'm done now. Thank you.
All right, not a problem at all. Thank you for letting me know. All right, so let's go to the next page. All right, so once again, first thing I did over in the left box is wrote down all of our given pieces of information. Population mean was 30. Population standard deviation was 12.9. Sample size was 35. And then our sampling distribution mean was 36.2. Or sampling distribution was 36.2. All right, then the mean is going to be the same as the mean of the population. That's going to be 30. Then we take the standard deviation of the population, 12.9 divided by the square root of 35. That'll give us 2.180498. So I always go out 4 or 5 decimal places just to be as accurate as possible when there's a run-on decimal. Really, you shouldn't go 2 decimal places throughout your calculation, because the more you round something off and then the more calculations you add to it or apply to it, the further and further you get away from the most accurate answer possible. So I always go about 4 or 5 out in my calculation, and then notice in the z-score, you do the work and then you round it to 2 decimal places at the end. After you've done your calculation, that's when you round it to your 2 decimal places. So we have to find our z-score, doing 36.2 minus 30 divided by the 2.180498, and that'll give us 2.84. All right, then we go to the chart. 2.84 chart value gives us 0.9977. And once again, there's a reminder that whatever the chart gives us is always less than. So that's what that is for. All right, so since we want to know how unusual this is, then we want to know the chance of it being greater than. So we take that 9.9977 and subtract it from 1. And you see our answer is 0.0023. All right, and this is unusual because the probability is less than 5%. Remember, we talked about that before in previous section, that something is less than 5%, 5% was going to be our marker. The 5% to 0.05, that is going to be considered unusual. And we have 0.0023. So that means that this is considered unusual. All right, any questions or problems before we go to the next page? All right, can we scroll or go to the next page? I see a thumbs up. Anybody else? All right. All right, so that was it for 8.1. That's the process that they emphasized in 8.1. Questions before we look at 8.2? All right, come on, scroll down. So distribution of the sample proportion is 8.2. Make sure. Yep. So before we looked at the distribution of the sample mean, now we're looking at the distribution of the sample proportion. So suppose that a random sample of size n is obtained from a population in which each individual either does or does not have a certain characteristic. The sample proportion is given by, this is what we call p hat, when you have that little kind of like a triangle, part of a triangle over top of your variable is that variable hat. So this is p hat. So you would take x and place it over n. X is going to be the number of individuals in the sample with the specified characteristic, and the sample proportion is the statistic that will estimate the population proportion. All right. And then down here, P is going to be your population proportion. P hat is your sample proportion. All right, we're good to go to the next page. Why is it not going for me? There we go. All right, computing a sample proportion. So the Harris poll conducted a survey. Whoa. Okay. There you go. The Harris poll conducted a survey of 1,200 adult Americans who vacationed during the summer and asked whether the individuals plan to work while on summer vacation. Of those surveyed, 552 indicated that they plan to work on vacation. Find the sample proportion of individuals surveyed who plan to work while on summer vacation. All right, so sample size is 1,200. It said the survey of 1,200 adult Americans, so that's your sample size. And then the characteristics that we're looking at are those who plan to work while on summer vacation. So out of the survey, those surveyed, which were, in other words, out of the 1,200, 552 indicated that they plan on working on vacation. So to find the population proportion, you would just do X over N. P hat is X over N, 552 over 1,200, which reduces to, or divides out to give us 0.46. All right. Any problems with that? So I had this last statement, conclusion of what they're talking about. The Harris poll estimates that 0.46 or 46% of adult Americans who vacation during the summer plan to work while on vacation. So that's what that would mean. All right, everybody good before we go to the next page? All right, so sampling distribution of p hat for a simple random size of n, of size n, with the population proportion of p. The shape of the sampling distribution of p hat is approximately normal, provided that n times p times 1 minus p is greater than or equal to 10. So remember, if it's approximately normal, once again, it means we can use our z-scores. So that's why this is important to establish this. N times p times 1 minus p is greater than or equal to 10. The mean of the sampling distribution of p hat is going to be the same thing as p, very similar to what we did last section. And then the standard deviation of the sampling distribution of p hat is going to be p times 1 minus p over n, and you take the square root of that. All right, let's look at an example. According to, oh, I spelled national wrong. Okay. According to the National Center of Health Statistics, 15% of all Americans have hearing trouble. All right. So A, in a random sample of 120 Americans, what is the probability that at most 12% have hearing trouble? Then B, suppose that a random sample of 110 Americans who regularly listen to music using headphones results in 26 having hearing trouble. What might you conclude? So I'll give you a chance to write that, and then we'll look into it. All right, anybody still copying? All right. Ah, here we go. So first thing we want to establish is our sampling distribution approximately normal. So N is 120. That was our sample size. P is 15%. So you convert that to a decimal as 0.15. So you do 120 times 0.15 times 1 minus 0.15, which would have been 0.85. When you multiply those together, we get 15.3, which is greater than 10. So since 15.3 is greater than 10, the sampling distribution is approximately normal, and that means z-scores can be used. All right, so scrolling up. So in A, we were asking for, matter of fact, let me go back, answer the question. The random sample, 120 Americans, what is the probability that at most 12% have hearing trouble? Okay, just want to make sure. So we're looking for at most 12% having hearing trouble. So that means the characteristic we're looking at is 12%. That's P hat for us. That's the one we're in question. That's in question. At most 12% have hearing trouble. So that's 0.12 for P hat. The mean of our sample proportion is going to be at 15% because that's the same as the population proportion. So that's 0.15. Then to find the standard deviation of a sampling proportion, we do P times 1 minus P over 120. Made a mistake right there and I put the square root of n, so I tried to block that out, but it's just regular n, not the square root of n. So then it's 0.15 times 1 minus 0.15 over 120. Then take the square root of that, that would be 0.032596. All right, then we find our z-score. P hat minus the mean of our sampling proportion divided by the standard deviation of our sampling proportion. And it's 0.12 minus 0.15 over that 0.032596, which will ultimately give us negative 0.92. Once again, don't forget to round your z-scores to 2 decimal places. And then we can go to the chart. Go to the chart, you'll find the chart value of 0.1788. All right. So since the question asked about at most, this means we want less than, because at most means at the most 12%. So 12% and everything under that. So the chart value is the answer. So this means the probability that a random sample of 120 Americans results in at most 12% having hearing trouble is 0.1788. You know, if it had said at least, that means the least is going to be the 12%, and then everything greater, then we would be looking for more than or greater than. But since we said at most, we were looking for less than. Any questions? All right. Can we move off this page? Anybody? Still copying? All right. See a thumbs up. Thank you. So then we got to do B. I can get my notes to go right. So B, suppose that a random sample of 120 Americans who regularly listen to music using headphones result in 26 having hearing trouble. What might you conclude? Come on, scroll down. There we go. So in this one, they don't give us the proportion, the sampling proportion. We have to, which is p hat. So we have to calculate that because they said 26 out of that sample experience hearing trouble. So that's 26 over 120 for our p hat. Before in A, they gave us the percentage, which was 12%. This time they told us 26 out of the 120 had this characteristic of hearing trouble. So that'll be 0.217. All right. So p hat and our not p hat, sampling mean and standard deviation of our sampling with the mean or sampling proportion and the standard deviation of our sampling proportion was already calculated in A. So that's why we got a 0.15, 0.032596. We can use this information to find our z-score, which is 0.217 minus 0.15 divided by the 0.032596. That'll give us 2.06. And the z-score chart gives us 0.9803 from that z-score. All right. Here, since the question asks, what might you conclude? We should explore greater than to see how unusual it is. So remember, whenever we're trying to find greater than, we'll take the chart value, subtract it from 1. We have 0.0197. All right. So the proportion, once again, this we're talking about comparing it to 5%, 0.05. So the proportion is less than that 5%. This means it is an unusual occurrence. The results obtained are unusual, and that is our conclusion. All right, questions. All right, is everybody finished copying? Make sure we're good. All right. Let's see, to have one more page. Oh no. Hold on. Did it again. Hold on, guys. I'll go. Let's do this one. All right, so this is finishing off that problem. Magnify it. There we go. All right, so you can make one of two conclusions. The population proportion of Americans with hearing trouble who regularly listen to music using headphones is 0.15, and we just happen to randomly select a higher proportion that have hearing trouble. So that is an option. But then the second option is that the population proportion of Americans with hearing trouble who regularly listen to music is using headphones. Regularly listen to music using headphones is more than 15%. So the second one is more reasonable. So in other words, the fact that they're regularly using headphones contributes to hearing loss. You know. All right, any questions on anything I've written so far? Is everybody good? All right. See one thumbs up. That is cool. Appreciate it. Thank you. So, if I'm not mistaken, that is it for, yep, that is it for 8.2. So now it's about you guys getting in there and trying out the process. If you follow the steps and the procedure, it should be okay. But you never know, something might come up and you say, hey, I don't quite understand this or whatever. And if you don't have any questions today, even from previous sections, we got all of next week that we will have the floor open for questions.
Did 8
And
points? Oh, sorry.
no, go ahead. You're fine.
Did 8.2 start with the example, or like where did 8.2 start? Because
Sampling
distribution.
Distribution of your
P
sampling
hat.
portion right here. Yep.
Okay. I did actually have a question on the homework.
Mm-hmm.
On the homework from last chapter though.
Okay. All right.
It's
I will go ahead and change to the notes, to my note page, I mean.
It's 6.2 question 10, part C.
Okay. So let me see if I can pull it up. Almost there. Didn't have my math lab up, so. And he says 6.2.
Question 10, part C.
Okay.
And so I was using a binomial probability calculator to do it. And I understand the probability, but I was just having issues with the X value and I forgot what the other one was.
Okay, let me get to it. I'm there, but I have to get all the way to C.
And then I understand the concept with the 1%. I understand like what the question's asking and everything, but I guess I wanted to know how the X value and the other value, like what to plug in for those, because I think one of them you had to do above. So it's saying, for example, like part C says for a plane with seating capacity of 255 passengers, what is the largest number of tickets that can be sold to keep the probability of a passenger being bumped below 1%? So I know that I'm looking for like 0.01 or below, but for the, I think it was the X value, it's set to put in 256. So it's a number over 255. I just wanted to know, like, or if you could like walk me through.
Okay, so
a
let me
different
go.
problem, because
Right, let me look at the one I have. Where mine have, mine, I guess mine's going to be similar, but not the same numbers. So it says, suppose that the probability that a passenger will miss a flight is 0.1055. Airlines do not like to bump flights, right? Desirable both flights because passengers must be bumped from the flight. Suppose that an airplane has seating capacity of 49 passengers. So how many was yours capacity at? Mine's capacity at 49 passengers.
yeah, and the question is 49, but it's for part C.
Okay.
So part C is saying the seating capacity is 255.
Gotcha. Okay. So 51 seconds or so, what's the probability that 50 and show up in the flight? And you say you were good with A and B, so suppose that 55 tickets or so for a plane seating capacity of 255. What is the largest number of tickets that can be sold to keep the probability passenger being bumped below 1%?
Because I think it had us guess like the number of trials. We just had to like put in numbers and see what the percentage was. But I just wanted to know, like, more so, I think it was the X value that was a number above the capacity. Is it always going to be a number above what it's saying? And why is that?
Let me look. Let me put it in my thing. So we got plane capacity 255 at cap. %. This flight. right, so let me go to binomial. Probability of success on the trials, the number of trials. Hold up, where it go again? Right, so we don't know what X is. Want to be less than 1%. I'm pretty sure I can put it in the formula. 0.01. Because you could guess it or you could put it in a formula. Okay, now this won't. Thank you. 0.1005. So one second, just trying to put this in before I give you my answer. I want to make sure I'm correct when I do it. All right, so we the only ones up. Everybody did. Okay. All right, so no tickets will be sold while keeping probability. I'm trying to get these numbers that they have according to this calculator, and then I'll be able to. All right, 273, yeah, and 0.0093. Did I put the number in wrong? How am I getting 0.0? Yeah, okay, there it goes. Greater than 0.0093. And then the other one, 74. Greater than 0.0158. Come on, man. All right, okay, we good. Yeah. So looking at the explanation, they just wanted you to keep, that's why they said use technology. They wanted you to keep putting it in there and see. And I'll show you. All right. So, you know, you talking about the probability of success would be 0.8945. So for mine, they gave me the probability of missing the flight is going to be 0.1055. So if you want to know the probability of making the flight, then you subtract it from 1, and that's why I have 0.8945. And so If you're talking about making the flight, you're talking about the probability. If you're going to get bumped, that means that 255 people had to make the flight because that's your capacity. So that's why I have two number of successes, 255, and then the number of trials. So really, the way they showed it in the explanation, yeah, like you mentioned, you're supposed to pretty much, be put in values. You can start with 255 and see how it changed. Of course, that's going to be 100%, but then you start adding and see when it's going to get to, 1%, and you probably would jump up to 270 or
So
260.
for the probability, you don't always subtract what they gave you from 1.
It depends on what you're trying to do. So now let's go back to this problem. It depends on the given information and what you're trying to do. So if you go back to the problem, they give you, suppose the probability that a passenger will miss the flight. That's the percentage right there, the chance that you will miss your flight. So that means when you subtract that from 1, that's the probability that you will make the flight. And so if you're talking about being bumped, the reason why you're bumped is because everybody made the flight. You see what I mean? So that's why you have to explore. That's why you have to change your probability.
Well, I always,
Mhm.
mine looks pretty similar to yours, and I always use the same probability. Like, took that number -1 or from 1 and used that same probability, and I got the right answers for all of them.
You talking about for this problem?
Yeah, I didn't have that specific problem, but
No, but I'm talking about for this number 10.
uh-huh.
Yeah, but that's what I'm saying. That's what you were supposed to do in this problem.
Okay.
Yeah.
Well, I was saying for part C, I was just confused because I thought it was always you take that number, subtract it by 1. So I thought I already knew that one, but I was just confused with what values to put in for the for X and for the number of trials.
Oh, well, no, they said that the probability, if you look at the statement, the probability that a passenger will be bumped if 267 tickets are sold is this probability right here. And that's less than 0.01. So now what you're trying to do is get the highest number of tickets that you can sell and still be under 1%. And so you just keep running it up. That's why it says, where is that? I don't know, I saw somewhere where it says use technology. But yeah, so that's what you would have to do. You would just, keep plugging in numbers until you get to, and notice how they said right here, for 200, can I highlight it? Yeah, for 273
But
tickets. Okay, go ahead.
when I guess, do I plug that number into the number of trials or the number of successes?
Number of trials. Number of
Okay,
trials,
and then what do I put for the number of successes? It's a
255.
number above 255.
No, you can just use 255 because that's your capacity.
Okay, so I use 255.
Mm-hmm. So let me go back to my, where it go? Right here. So notice I got 255 right here. And this is the number that I keep changing. So 273. And so my number changed, and where it go? What was the number? I think it was the greater than. So right here is a value that they're referencing. That's under 1%. But then if I were to go to 274, then I go over 1%. So that's why they say the most that you can sell and keep a 1% chance that people will get bumped would be 273 tickets. Because right here, when you round this up, this still would be under 1%. This would be 0.93%.
Okay, well, I'm still kind of confused because I'm looking at the problem that I already did, and I'm using the a probability of success. The number of trials is what is I already got the answer right. It's 286, so I put that in for the number of trials, and then for the number of successes, I kept the 255, which is the capacity. Or no. Let me see. Hold on. I don't think it's 255. It's 270. Okay, okay, so it's giving me 0.015, so I don't round up.
All right, so now what's your cap is 270?
270
and you did 286.
for the number of childs and 0.9072.
And so now, what do you
There's
count?
a different.
Mhm.
It's a different probability of success.
Oh, right. What's your probability of success?
0.9072.
9072. Okay, that's what you were saying, that you had your probability of success. Okay, so here I'm looking at 0.8, right? And then if you were to go to 287, right, and that'll take you over, that'll be 1.5%. Right, so 286 would be your answer, because that keeps you under 1%.
I'm not looking at the last one. I'm looking at the second one.
Well, when you say last, the second, you're talking about second to last?
Mhm.
Oh, yeah, you're talking about this probability right here.
Mhm.
Yep.
Okay, because I know in the example it showed the last one. It showed. Okay.
Because remember, you're talking about being greater than 270. So in other words, remember, your cap is at 270. So what's the probability of 271 happening, 272 happening, 273? Because 271 on up are going to be bumped because there's no more room. So that's why you're looking at the greater than.
Okay.
Does that make sense? Is that good?
Yeah.
Okay.
I'm gonna just take notes on it.
Okay. So like I said, when you do this, you're looking at the greater than, because you're talking about being greater than 270. Because if you're greater than 270, that means that people are going to have to be bumped, because everybody, the plane is at capacity.
Yeah, I was more so confused of where each value went into for the number of childs and
Gotcha.
X. But
Gotcha.
I got that part.
Okay, cool.
Okay. Thank you.
Not a problem. You have a good one.
You too.